Okay, Assalamualaikum and hi everyone. ENT 286 Instrumentation and Measurement. This is the video lecture for Chapter 4, Signal Characteristics and Conditioning. So in Chapter 4, we will learn in detail regarding the characteristic of signal as well as the condition that we have to consider for each signal. Okay, signal actually can be defined as the sequence of state in a communication channels or codified message. In communication system, a transmitter will be used to encode any message into signals carried by communication channels. For example, if we use the telephone to speak and say hello, the word will be converted into signal by the telephone transmitter, transmit by wires to the receiving telephone, then reconvert the signal into sound by the receiver. There are various signal waveforms such as static, dynamic, step, and ramp, and each of signal waveform can be represented by a mathematical equation formula as you can see in the slide. Signal can be categorized in various ways, but the most common is continuous and discrete time signals. Discrete time signals are often referred to as a time series in other fields. Continuous time signals are often referred to as continuous signals, even when the signal functions are not continuous, as examples square wave signals. A second important distinction is between discrete value and continuous value. Digital signals are discrete value but are often derived from an underlying continuous value physical process. If for a signals, the quantity are defined only on the discrete set of time, we call it a discrete time signals. In other words, a discrete time real signals can be seen as a function from the set of integer to the set of real numbers. A continuous time real signals is any real value function which is defined for all time t in an intervals, most commonly an infinite intervals. Less formally than the theoretical distinction mentioned above, two main types of signal encountered in practice are analogs and digitals. In short, the difference between them is the digital signals are discrete and quantized, while analog signals possess neither property. One of the fundamental distinctions between different types of signals is between continuous and discrete time is set of real numbers, whereas the domain of a discrete time is set of the integer. Discrete time signals often arise via sampling or quantizing of continuous time signals. For instance, sensor output data continuously, but since a continuous stream may be difficult to record, a discrete time signal is often used as an approximation. Quantization is the process of approximating a continuous range of value by a relatively small set of discrete symbols or integer value. For example, rounding a real number in the interval between 0 to 100 to an integer starting from 0, 1, 2 to 100. If a signal is to be represented as a sequence of numbers, it is impossible to maintain high precision. Each number in the sequence must have a finite number of digits. As a result, the value of such a signal are restricted to belong to a finite set. In other words, it is quantized. This slide shows the difference between three types of signals: analog signal with continuous time varying, digital signal with large time division, and digital signal with small time division. There are a few examples of signals in our daily life, such as motion, sound, compact disc or CD, picture, and video. Advantages of digital signals compared to analog signals. Increasing the number of the time deviations in a digital signals can make the digital signal nearly as smooth as analog signals. Digital signals are much easier to store than analog signals and are much less prone to degradations. By definition, each piece of information in a digital signals is a number, easily distinguished from other numbers. One analog, one analogy for a digital signal could be tables of numbers, and comparables analogy for an analog signal would be a graph. It is much easier to accurately copy a tables than a graph. Signal modulation, example of signal manipulation. An information signal without modification to be sent somewhere may not be able for transmission. This is because the signals are usually a voltage that varies with time. To avoid large signal loss, the information signal must be used to vary the carrier signal that is more technically appropriate, which has the frequency, spectrum, and power needed for the applications. The process is called modulation. Modulation definitions is the process of encoding a baseband source signals or information signals into a carrier signals. The carrier waveform is varies in a manner directly related to the baseband signals. The carrier can be sinusoidal signals or a pulse signals. The result of carrier signals is called the modulated signals. A device that performs modulation is known as a modulator, and a device that performs the inverse operation of modulations is known as the demodulator. A device that can do both operations is called a modem. Low frequency information signals is put in high frequency sine wave, which produce a waveform that's suitable for transmission. AM and FM are two of the most popular modulation techniques. We will discuss the difference of AM and FM in the lecture. This slide shows the difference of each signals when we convert the digital information signal by using AM, PM, and FM. As a summary for this subchapter, signal characteristic, we can say that a signal can be in discrete or continuous form, widely known as digital and analog signals, convey information, can be transmit and receive, can be in any space, can be processed, and importantly, can be measured. The second part is signal conditioning, or in the general measurement system block diagram, we call it as signal modification subsystem. Signal from detector or sensing stage has to be modified in order to make it more usable. This signal is then to be used in later stage of system that may consist of processing element. proper selection of signal conditioning circuit can improve the quality and system performance. There are many possible functions of the signal conditioning stage. The following are the most common, which are amplification, attenuations, and filtering. Okay, number one, amplifications. Required in the system to improve the signal strength, which is typically in the low level range of less than a few millivolt. The amplitude can be increased using a device called an amplifier, as shown as a block diagram in the slide. The low voltage signal, Vi, appears as a differential voltage on the input side of the amplifier. On the output side of the amplifier appear a higher voltage V0. The degree of amplification is specified by a parameter called the gain G. Gain is the most commonly stated using a logarithmic scales, and the result is expressed in decibels, dB. For voltage gain, this takes from the form G in decibels equal to 20 log G, where G is equal to V0 over Vi. Although increase in signal amplitude is the primary purpose of an amplifier can affect the signals in a number of other ways. The most important of these are frequency distortion, phase distortion, common mode effect, and source loading. In the figure, show the frequency response of an amplifier plot as gain in dB versus the log of the frequency. Typically, the gain will have a relatively constant value over a wide range of frequencies. However, at extreme frequency, the gain will be reduced. The range of frequency with close to constant gain is known as the bandwidth. The upper and lower frequency defining the bandwidth called the corner or cut-off frequency are defined as the frequency where the gain is reduced by 3 dB. Another important characteristic of amplifiers is known as common mode rejection ratio, CMRR. When different voltage are applied to the two input terminals, as shown in the figure, the input is known as the differential mode voltage. When the same voltage relative to ground is applied to the two input terminals, the input is known as a common mode voltage. The measure of the relative response to differential and common mode voltage is described by common mode rejection ratio, defined by CMRR equal to 20 log G differentials over G common mode, where G differential is the gain for differential mode voltage between input terminals, and G common is the gain for common mode voltage applied at the both terminals. Signal amplifier can be constructed using a common low-cost integrated circuit component called an operational amplifier, or simply NOM. NOM is represented schematically by a triangular symbol as shown in the slide. The input voltage, Vn and Vp, are applied to the two input terminals labeled negative and positive, and the output voltage, V0, appear through a single output terminals. There are two power supply terminals labeled V positive and V negative. Operational amplifier notation and parameter. The circuit symbol for an OM is shown where V positive is non-inverting input, V negative is inverting input, V out is the output voltage, Vs positive is positive power supply, Vs negative is negative power supply. Gain A is equal to V out over V in, where V in is equal to V positive minus V negative. In the single operational amplifier datasheet, there are a few terms that be listed such as input offset voltage, input offset voltage adjustment range, input offset current, input bias current, input resistance, and input voltage range. Input offset voltage is a voltage that must be applied to one of the input pin in order to give zero output voltage. Input offset current is difference of two input bias current when the output voltage is zero. Input bias current is an average of both current flowing into both of the inputs. Input resistance is the resistance of the operational amplifier at either input when the other grounded. Input voltage range is the voltage that common to both input and ground. As for the output parameters, a few terms such as output short circuit current and output voltage swings can be found in the datasheet where output short circuit current is the maximum output current that the operational amplifier can deliver to the load. Output voltage swing is the maximum output voltage that the operational amplifier can give without distortions or clipping. This depends on the load resistance, while the output resistance is the resistance at the operational amplifier's output. And last but not least, last signal voltage gain, slew rate, supply current, common mode rejection ratio, CMRR, and power consumptions. Where the large signal voltage gain is the ratio of the maximum voltage swing to the change in the input voltage required to drive the output from 0 to the specific voltage. Slew rate is the rate of change of the output voltage with the operational amplifier having a unity gain. Open loop voltage gain is the output voltage to input voltage ratio of the operational amplifier without feedback. Supply current is current that the operational amplifier withdraw from the supply. Common mode rejection ratio is a quantifier of the ability of the operational amplifier to reject signals that are simultaneously present at both input, while bandwidth is usually specified as unity gain bandwidth. And the power consumption is the power consumed by the operational amplifier when operated. A simple amplifier using an OM called a non-inverting amplifier is shown schematically in the slide. The term in non-inverting means that the signal of the output voltage relative to ground is the same as the input voltage. This OM is called as the non-inverting amplifier because input signals is connected to positive sign. And it has a feedback loop, which is a closed loop configurations. For the application purpose, the input impedance is nearly infinite and the output impedance is nearly zero. The circuit is ideal for sensors that have a high source impedance, and those would be affected by the current draw of the data acquisition systems. For analyzing parameter, we will use V0, R1, R2, and the ground, and also current and voltage from nodes B. What for gain derivations, and what happens if gain is equal to 1? If gain equal to 1, no term for resistor, and it has a unity gain with the high impedance. Therefore, V in is equal to V out. For the function purpose, an impedance transformer in the sense of converting a voltage at high impedance to the same voltage at the low impedance. This slide shows the gain derivation for non-inverting amplifier. The degree of amplification G for non-inverting amplifier given by G is equal to V0 over Vi equal to R1 plus R2 over R1. Therefore, G for non-inverting amplifier is equal to 1 plus R2 over R1. From the derivation, we note that its gain is depend on the resistor ratio of R1 and R2. If Vi is high enough, V0 will approach the power supply Vs. Increasing Vi will no more increase the output V0. This is called as output saturation. The range of frequency between f equal to 0 and Fc is the bandwidth of the amplifier. Above Fc, the gain starts to decrease or roll off, and this roll off occurs at a rate of 6 dB per octave. This roll off in gain at high frequency is an inherent characteristic of OM. The cut-off frequency Fc depends on the low frequency gain of the amplifier. The higher the gain, the lower is Fc. This low frequency gain cut-off frequency relationship is described by a parameter called the gain bandwidth product, GBP. For most OM-based amplifier, this product of the low frequency gain and the bandwidth is a constant. Since the lower frequency limit of the bandwidth is 0, the upper cut-off frequency can be evaluated from Fc equal to GBP over G. The value of GBP normally will be given in datasheet. Another common OM circuit called the inverting amplifier is shown in slide. This circuit is called inverting because the output voltage relative to ground is of sign opposite to the input voltage. Inverting amplifier form the basis for many other OM circuits, including filters and integrators. This circuit is called as the inverting amplifier because the input signals is connected to negative sign. It has a feedback loop, which is closed loop configurations, and it used in many other OM configurations such as an active filter, integrator, and differentiators. For application purpose, the configuration allowed the level of sensor output to be matched to the level necessary for the data acquisition system. The input impedance is approximately infinite and the output impedance is nearly zero. Thus, this circuit provides impedance transformation between the sensor and the data acquisition systems. For the analyzing purpose, we will use V0, R1, R2 and the ground, and also current and voltage from node B. The degree of amplification G for non-inverting amplifier is given by G equal to minus R2 over R1. This circuit is the modifications of the inverting amplifier and we call as the summing amplifier. It used as a summing amplifier that sum two or more input voltage. The output voltage is equal to negative R2 over R1 times V2 plus R2 over R3 times V1. Inverting amplifier has similar frequency properties with non-inverting OM, which are GBP equal to R2 over R1 plus R2 GBP, and phase shift is equal to negative tangent minus 1 times F over Fc. In some cases, a measurement will result in a voltage output with an amplitude higher than the input range of the next component. The voltage must then be reduced to a suitable levels and a process known as the attenuations. The simplest method is to use a voltage dividing network as shown in the slide. The resulting output voltage from this network is V0 equal to Vi times R2 over R1 plus R2. Filter is the network used to attenuate certain frequency but allow others without attenuations. It consists at least one passband, which is a band of frequencies that the output is approximately equal to input, and attenuation band that the output is equal to zero. Cut-off frequency is the frequency that separates the various band and attenuation bands. Important characteristics of filter networks is its construction make use of the purely reactive elements. There are two types of filter, which are passive filter and active filter. Passive filter only use passive circuit components such as resistors, capacitors, and inductors, while active filter use active elements like operational amplifier in addition to passive elements like resistance, capacitance, and inductance. Both of passive and active filter can be classified as follows. Low band filter deliver low frequency and eliminate high frequencies. High pass filter send on high frequency and reject low frequency. C and D show the band pass filter pass some particular range of frequency and discharge other frequency outside the band. And last but not least is band stop filter, stop a range of frequency and pass all other frequency. Passive filter, low pass filter is block high frequency and pass low frequencies. The either LPF is signal above cut-off frequency Fc are simply rejected. In terms of resistor and capacitor, cut-off frequency Fc is given by Fc is equal to 1 over 2 pi Rc, and gain is given by A equal to 1 over set 1 plus Fc over F over Fc squared. At low frequency, the capacitive reactance is very high. Therefore, the capacitor circuit acts like an open circuit. At very high frequency, the capacitive reactance is very low. Therefore, V out is very small compared to V in. Passive filter, high pass filter. Pass high frequency, blocks and rejects low frequencies. For either high pass filter, signals below cut-off frequency Fc are simply rejected. In terms of resistor and capacitor, cut-off frequency Fc is given by Fc equal to 1 over 2 pi Rc, and gain is given by A equal to F over Fc over surd 1 plus F over Fc squared. At low frequency, the gain is small. Therefore, V out is small compared to V in. As the frequency goes high, the gain approaches unity. Passive filter, bandpass filter. Its block frequency below a low limit and above a high limit, while passing a frequency between the limits. Can be constructed by cascading low-pass filter and high-pass filter. At frequency below the pass band, band-pass filter behave like high-pass filter, while above the pass band frequency, the band-pass filter act like low-pass filter. In pass band, the band-pass filter circuit is almost as a resistive network. Thus, gain is given by A equal to R2 over R1 plus R2. Lower cut-off frequency, Fc lower, is equal to 1 over 2 pi R2 times C2, while for upper cut-off frequency, Fc upper is equal to 1 over 2 pi R1 times C1. Passive filter, bandstop filter, is block a specific range of frequencies. Can be realized but not very effective one. Simple RC combination, also known as notch filter. The circuit is called as twin T filter. In twin T bandstop filter, at the very low and high frequencies, the gain is almost unity. But between the two, there is a frequency where the gain becomes zero. The frequency is known as notch frequency F naught, where F naught is equal to 1 over 2 pi Rc. Active filter. Generally, the impedance are used in the inverting amplifiers using operational amplifiers. Basic relationship can be used to obtain the desired filter section is as follows. V0 over V1 equal to ZF over Z1. Advantages over passive filters. Inductors can be avoided. Passive filter without inductors cannot obtain a high Q or low damping, but with them are often large and expensive, may have significant internal resistance, and may pick up surrounding electromagnetic signals. The shape of the response, the Q quality factor, and the tune frequency can often be set easily by varying the resistor. In some filters, one parameter can be adjusted without affecting the others. Variable inductance for low-frequency filter are not practical. The amplifier powering the filter can be used to buffer the filter from the electronic component it drives or is fed from, variations in which could otherwise significantly affect the shape of the frequency response. So that's the advantages of active filter over passive filter. Active filter, low pass filter. For low pass filter circuit, V nodes is given by minus RFH over R1H times 1 plus j omega RFH times CFH times C1, where omega H equal to 1 over RFH times CFH. H is referred to the characteristic high frequency. Active filter, high pass filter. V0 is given by minus j omega RFL times C1L over 1 plus j omega R1L times C1L times V1, while omega Ls is equal to 1 over R1Ls times C1Ls, and Ls refer to the characteristics of low frequency. Active filter, low pass filter, non-inverting OM configurations is V nodes is given by RF plus R1 over R1 times 1 plus j omega RH times CH times V1, and omega H is equal to 1 over RH times CH, and H refer to the characteristic of high frequency. Active filter, high pass filter, non-inverting OM configurations. V node is given by RF plus R1 times j omega RL times CL over R1 times 1 plus j omega RL times CL times V1, where omega Ls equal to 1 over RL times CL, and L refer to the characteristic low frequency. And last but not least, active filter, band pass filter. V nodes is given by RF2 plus R2 times RF1 plus R1 times j omega RL times CL over R2 times R1 times 1 plus j omega RL times CL times 1 plus j omega RH times CH times V1. So that's all for the theory part in chapter 4. How to use the equation and formula will be discussed further during our lectures and tutorial. So thank you for now. Goodbye.